Hello, class, and welcome to the next module in 8th grade Eureka Math. We're in Module 3 now. Today is the first day. It's Lesson 1, all about same shape. So in Module 2, we talked about same shape, same size. Module 3 is about same shape, something called similarity that we're going to be talking about a lot today. So because this is a new module and kind of a new concept talking about similarity, you might need to, there's going to be a few extra notes today. The notes are going to be a little bit long, just introducing you to the rules of similarity and how similarity works. So make sure you have a couple pages to take notes on and that you're ready to go. Make sure also you have pages 1 through 11 of your Module 3 book ready to go so that we can work well on this. So it's all about same shape today. So Module 2 taught us about congruence. And Module 2 congruence was same shape, same size. And we learned in Module 2 how things stay congruent. We learned about rigid motions. We learned about translations, reflections, and rotations. And those three things kept things the same shape, same size. Module 3, we're going to talk about similarity. It's like congruence in that the shape has to be the same, but the size can be different. Similar shapes can have to have the same exact shape, but the size can be smaller, larger, or the size can even be the same. So congruent shapes are similar, because the shape is the same and the size can be the same. But similar shapes can be bigger, similar shapes can be smaller, similar shapes can be any size. As long as the shape is identical, the size can be different and it is still similar. It is still similar. So today we're going to explore similarity a little bit. We're going to look at some shapes and talk about whether or not they're similar. And then we're going to talk about the rules for similarity. Because just like in Module 2, translations, reflections, and rotations had rules. Congruence had rules. Similarity also has rules. So Lesson 1 is basically rule day. We're going to learn about the rules of similarity. So let's start exploring this a little bit. We're going to do an exploratory challenge on pages 1 and 2 of your workbook. So if you need to, you can pause the video and finish copying down the notes. And then you can unpause the video when you're ready to move on to the exploratory challenge. But I am going to move to the exploratory challenge on pages 1 and 2 right now. And there we go. Here's what the exploratory challenge looks like. They give you, it's on pages 1 and 2. They give you 8 pairs of shapes, 8 pairs, pair A, pair B. And the instructions tell you 2 geometric figures are said to be similar if they have the same shape, but not necessarily the same size. Using that informal definition, are the following pairs of figures similar to one another? So are these similar? So you can answer in your head, or you can listen along with me. You can work ahead if you like. So pair A, are these similar? Are they the same shape? And the answer is yes, they are similar. Explain. Yes, they are the same shape. Just different sizes. And already you see the difference between Module 3 and Module 2. Because in Module 2, they'd ask, are these congruent? And these are not congruent, but they are similar because they are the same triangle. This triangle just got increased in size to make this triangle, and this triangle can decrease in size to make this triangle. Same triangle. And the way you know they're the same is the ratios of the sides are all the same. Let's look at pair B. Pair B. Are these figures similar? Are these the same shape? The answer, you might say, well, they both have 4 sides, but they are not similar. Because this has 4 equal sides, a square. This does not have 4 equal sides, it's a rectangle. One is a square, the other a rectangle. They are not the same shape. They are not the same size. They are not similar. It's that simple. 4 equal sides, not 4 equal sides. Pair C, we have some pentagons. Now, are these similar? Are they the same shape? Yes, they are similar. These, in fact, are special because they are similar and they are congruent because they are the same shape and the same size. They are similar and congruent. So pair A are similar because they're the same shape. Pair B are not similar because they're different shapes. Pair C are similar and congruent. So similar can be the same size. You remember that similar can be the same size. Pair D. Are these figures similar? Yes. They are both circles. They are the same shape. They are both circles. They're both the same shape. The only difference is the size. So hopefully you're getting it a little bit right now, where it's the shape that matters for similarity. Size is allowed to be different. Let's look at some trickier ones on page 2. Page 2, you'll see some different types of shapes, not the basic shapes anymore. Like pair E, we have these arrows. Are these similar? Yes, these are similar. They are the same shape. Is the size different? Yes. But the size does not matter for similarity. What about F and G? We're going to talk about together because they're all smiley faces. Now, pair F, are they similar? Yes, in pair F, they are similar. Same shape. But for pair G, they are not similar. Now you might be saying, Mr. Bear, wait, they're both smiley faces. Yeah, but if you look, this smiley face only got squeezed one way. This smiley face got, if you take this one and you shrink it, it shrinks in all directions. Everything gets shrunk. This one, it got smaller, but it only got smaller going this way. It did not get smaller going this way. So these are not similar. If you look at the rate, like if you look, the ratio is not the same. This looks like you just made the, like on a computer, how you can make some things bigger or smaller. This, you just made the smiley face smaller. This one, you just squished it. It's not, you did not make everything smaller, you just made it smaller up and down. So not the same smiley face. They're both happy faces, but they're happy faces in different shapes. That might have been a little bit of a tricky one. Remember, it has to be exactly the same shape. Size can change, but it has to look exactly the same. Pretend if you put it under a magnifying glass, would it look exactly the same? If the answer is yes, then it's similar. Now, pair H is a tricky one because you have not taken high school algebra yet. You, as an 8th grader, would say these are not similar because they are obviously different shapes, Mr. Baylor. Look at this one. This one looks more like a V, or like a valley. This one looks more like a big U-shaped valley. This looks sharper than this one. Well, they threw this one in just to trick you and give you a little bit of a preview of high school, because these shapes are what we call parabolas. And parabolas are special graphs. Like this graph might be the graph of y equals x squared. That's what it might be. This one might be y equals 4x squared. So actually, in high school, you're going to learn that, yes, these are similar. I know this is a tricky one. So if pair H is confusing you, just cross it out. Because pair H, they are actually, yes, they're the same shape. But when you grow a parabola, the parabola doesn't just increase and get bigger. The parabola actually, when it grows, it gets wider. A parabola, like when the smiley face gets bigger, it turns into a smiley face. When the arrow gets bigger, it's an arrow. Everything gets bigger. Everything gets bigger. When a parabola grows, it just gets wider. So parabolas follow a little bit different rules. Parabolas are kind of a funny, unique shape. But parabolas, when they grow, they just get wider. They don't get taller and anything. They just get wider. So these are the same shape because parabolas grow by getting wider. But that is a fact you're going to learn in high school. You don't need to worry about it right now. That was just a funny thing the book threw at you to show you that there are some things that are a little bit weird in math and to give you a little bit of a preview of what you're going to learn in high school. But that's the exploration activity. We're going to go back to the notes now, but what I'd like you to do before we go back to the notes is pause your video, look at the pairs A through H, and make sure you can understand by looking the difference between similarity, the difference between similarity and not similar, and the difference between similarity and congruence. I'd like you to pause the video and look for and make sure you understand similarity visually. Okay, class, hopefully you went back and looked at the pairs of examples on pages 1 and 2. Let's go back to our notes now. And this is where we stopped our notes. We stopped with exploratory challenge on page 1 and 2. But what I'd like to do now is, well, now you have a basic understanding of similarity. At least visually, you can probably identify it. You can look at it. So now that you have a basic understanding of similarity, let's discuss the rules of similarity. Because it's not enough just to, in math, remember, math is a science. Some people say math is the foundation of all science. So math relies on rules and structure and specificity. So we need to be specific when we're doing our math. So looking at something and seeing if it's similar or not, like we did in the exploratory challenge, is not always good enough. You need to be able to define it. You need to be able to measure it. You need to know the rules. So we're going to talk about the rules right now and how we measure similarity. So let's discuss this. Let's talk more about congruence, because for congruence, we used 3 rigid motions, and each of those rigid motions followed a rule. So you'll remember in Module 2, we talked about translations. And the rule for a translation was a vector. We also talked about the rigid motion, a reflection. And the rule for a reflection was the line of reflection. The third rigid motion we talked about were rotations. And the rule for a rotation was degrees and a center. So those were the rules for congruence. We had 3 rigid motions and everything has a rule. Well, similarity is going to be a little bit simpler than that because similarity really only has 1 motion. Similarity only has 1 transformation. And it is not a rigid motion. Not rigid motion because the size changes. Remember, in Module 2, rigid motions were called rigid motions because the size did not change. So similarity only has 1 rule that is not rigid because the size might change. So similarity's transformation is called a dilation. This is the 4th transformation you're learning about this year. You learned about translations, reflections, and rotations. Those are the rigid motions. This is the 4th transformation, the not rigid one. It's called a dilation. In simple terms, it's a size change. A dilation is just a size change. You might have even heard the word dilation before if you've ever gone to the optometrist, the eye doctor, because what they even dilate your eyes. Like if you've ever gone to the eye doctor and they've dropped those chemicals in your eyes to see in your eye better, and you have to wear the special glasses when you leave because everything is super bright. What the optometrist, what the eye doctor does is they give chemicals that make your eye, the black part of your eye, bigger. They make your pupil, the black part of your eye, bigger. They dilate your pupil. So it's when something gets, when the size changes. You might have even heard it if you've ever, if your mom or your aunt or somebody in your family are on a TV show, when someone's having a baby, they talk about how far dilated the new mom is. How big is the opening the baby's going to come out of? How much is the size of the opening changing? They talk about how big the dilation is. So dilation is a size change. So anytime something changes, the size changes, dilation. And so this is our 4th transformation. It is only for similarity. We have the 3 congruent transformations that are rigid. And we have the 1 similarity transformation, the dilation. So instead of learning 3 new things like we did in Module 2, Module 3, you just need to learn how to dilate. So let's talk more about dilation and its rules. Hopefully you got those notes copied. If you did not get these notes copied, remember my notes are posted on the Google Classroom, or you can go back, watch the video, and pause it later. But page 2 of my notes, we talk about more rules for the dilation. So just like rigid motions used rules, dilation also uses a rule. Dilations also use rules. And like the translation used a vector, reflection used a line, rotation used degrees. Dilation uses something called the scale factor. The rule for the dilation is called a scale factor. Now, the scale factor tells you how much everything grows or shrinks. Now, I underlined everything here because when we dilate a figure, we dilate every piece of the figure. Remember the smiley face in our exploratory challenge. Not everything changed in the smiley face. Only 1 dimension of the smiley face changed. Dilations change everything in the original. So the scale factor tells you how much those things change. Just like the vector told you where to translate, and the line of reflection told you what to flip over, and the degrees told you how much to rotate, the scale factor tells you how much something grows or shrinks. And it's everything in the original that grows or shrinks. And we're going to have lots of practice with this. I just want you to have the definitions in words right now. Now, for the scale factor, we also use the letter R. Instead of writing scale factor every time, mathematicians use the letter R to represent the scale factor. So in Module 2, if you see the letter R, they are talking about the scale factor. So if they say R equals 4, that means everything gets multiplied by 4. If you see R equals 1/3, it means everything gets multiplied by 1/3. So R is the same as the scale factor for Module 3. And so I wrote the rules. That's what the little red squiggly lines are for. The little red squiggly lines are to tell you the rules for R. So remember, every part of the original is multiplied by scale factor R. Every single piece, every side of the figure is multiplied by the scale factor R. If you have a smiley face, the eyes, the mouth, and the circle for the head all get multiplied by R. And it is multiplication. I underlined multiplication because we multiply by R. We do not add R, we do not subtract R, we do not divide R. It's called a scale factor, and factor means multiply. So we are multiplying everything by R. We multiply everything by R. So there's some rules you can remember. If R is bigger than 1, if R is greater than 1, that means we're multiplying by 2, 3, 4, anything, or even a fraction bigger than 1. The image grows. Because when you multiply by bigger than 1, the number gets bigger. Think about it. If you start with 2 and you multiply by 1, it stays 2. 2 multiplied by 2 grows. So if the scale factor is bigger than 1, the image grows. If the scale factor equals 1, the image stays the same size because you're just multiplying by 1 and 1 does not change the number. So R greater than 1, image grows. R equals 1, image stays the same size. If R is less than 1, so if R is a fraction, like 1/2, 2/3, 3/5, if R is less than 1, the image shrinks. So we're not dividing to make dilations smaller. We're multiplying by a fraction to make the images smaller. So these are the 3 basic rules about the scale factor. R greater than 1, the image is growing. R equals 1, the image stays the same. R is less than 1, or if R is a fraction, the image shrinks. Those are the rules for R. The other rule for dilation, there's another thing you need for dilations. If you're going to dilate, you need the scale factor. You also need the center to dilate from. You need to tell me where you are dilating from. Where does the dilation start? Where is the new image going? So you need how much and where. Kind of like for a vector. Vector told you how much and in what direction. Dilations, you need to know the same thing. Dilation, you need to know how much you're dilating and what direction you're going in. So those are the rules for similarity. I know it was a lot, but this is just an introduction. We're going to get a lot of practice doing this in Module 3, and we're going to do some more practice in just a minute. But I just want you to know the rules and have them written down so you have something to look at when we are discussing, when we are doing our work. So finish writing your notes down. If you need to, pause the video and go back and write down what you need. And then unpause the video when you are ready to work on some example problems with me. See you in a minute. Okay, class, welcome back. Hopefully you got caught up on the notes. Hopefully you are ready to work. We're going to do some practice right now on some of the skills that we just talked about, some of the rules for our similarities and dilations. So make sure you still have your notes next to you because we are going to refer back to them a couple times during these practice. But we're going to go back to page 2, which we were on before. We did the top part before, but there is an exercise 1, all the way at the bottom of page 2 that I want to talk about. So here we go. Given OP equals 5 inches, that means we have a segment that is 5 inches. So we can actually draw this if you want. This is where your ruler might come in handy. So you have O. Now I'm not going to draw it 5 inches because that's super long. How about I just do 5 centimeters? Or you know what? That's still pretty long. I'm just going to do it like that. Do it right there. So here we go. OP, and we're going to say that this is, I'm just going to label it 5 inches. So we have OP is a segment 5 inches long. And it is dilated by scale factor R equals 4. What is the length of OP prime? So it's dilated by a scale factor. Well, we go back to our rule and we see, okay, well, scale factor means we multiply. So we're multiplying by the scale factor. So we're multiplying by 4. And 4 is bigger than 1, so the image is going to grow. So we're actually going to take this and we're going to multiply this by, let me line it up, 4. And so this is P prime. So you see this one, we have 4 of these now. We multiplied it by 4. So here's the original segment OP. Here's OP prime multiplied by 4. Well, if we started with 5, what is the length of OP prime? What is the new length? Well, I know it was multiplied by 4. So OP prime is going to equal 20 inches. Because the original 5 got multiplied by 4 to make 20. So that's the answer. That's what happens. This is the answer. This is what it looks like when it grows. So this is similar to this. It just got bigger because we multiplied by a scale factor. For part B, now the scale factor is 1/2. So we're going to multiply by 1/2. And you look at our rules again in our notes. If R is a fraction less than 1, the image is going to shrink. So this time, let's make OP 5 inches. Here we go. So here's O, here's P, and it is 5 inches long. If we multiply by 1/2, 5 times 1/2, we do OP times R, which is OP times 1/2, and OP was 5 inches, so we do 5 times 1/2. So 5 times 1/2 is going to be right here, 2.5. So this is P prime. And I can even make this part red. So it's going to look probably purplish. But OP prime is going to be 2.5 inches because it got multiplied by 1/2. So this is how dilations work by what you can see. So dilation is just multiplying everything by the scale factor. The scale factor was 4, so 5 got multiplied by 4 to make 20. The scale factor is 1/2, so 5 got multiplied by 1/2 to be 2.5 inches. So when the scale factor is bigger than 1, it grows. When the scale factor is less than 1, a fraction, it shrinks. Goes from 5 to 20 or from 5 to 2.5. So that's a little bit of practice. That's a little example so you can see how it works. We're not going to be shrinking shapes in this lesson. We will do that later. In this lesson, we're going to be shrinking line segments, and we're going to be shrinking and growing line segments. So we will dilate shapes later in the future lessons in this module, but for this lesson, we're just going to dilate lines. Let's go to exercise 2 on page 3. So you can see that exercises 2, 3, 4, 5, and 6 are all going to use kind of this angle right here. We're going to use this diagram. So dilation from center 0. So here's our center 0. That's one of the parts of the rules. And we have the original right here. OP, the original, is 3, and OQ is 4. And so they labeled all of that for us. They labeled the center, they gave us the original, and they showed us P prime and Q prime. Now we're going to use what they gave us to answer some questions. So like number 2, if the scale factor is R equals 3, so the scale factor is 3, what is the length of segment OP prime? So R is 3, OP is 3. What's OP prime after the scale factor? Well, you know that OP prime is going to equal the scale factor times the original OP. That's how it works. We multiply. Remember, dilations in your notes, everything is multiplied by the scale factor. Multiply by the scale factor. It's in your notes. So we take the original and multiply by the scale factor. So the scale factor is 3, and OP, they told us, is also 3, which means OP prime, 3 times 3, is going to be 9 centimeters. So OP prime equals 9 centimeters. It is that simple to do a dilation like this. All you're doing is multiplying. That's it. For number 3, it says use the definition of dilation to show that your answer to exercise 2 is correct. This right here, they just mean show your work. So I did it right there. They said show your work. They just want you to do the answer first and then show your work. So we already showed our work up here. I'm not going to show my work again. But for number 4, if the scale factor is R equals 3, what is the length of OQ? So we did OP. Now they want us to do OQ prime. So this time, remember, it's asking for OQ prime. So OQ prime is going to equal the scale factor. And remember, in your notes, we multiply by the scale factor. So it's a scale factor times the original OQ. So look at the diagram. The original OQ was 4 centimeters. So OQ is 4. And they told us R is going to be equal to 3. So to find OQ prime, we just do 3 times 4, which is 12. So the original was 4. After the transformation, OQ prime turns into 12 centimeters. Just like that. Just multiply by the scale factor. That's all we're doing today, multiplying by the scale factor. And number 5 again says use the definition of dilation to show that your answer is correct. I already showed it up here, so I'm just going to show the work right there. There we go. You see all that? Hopefully you understood that, because we're going to work a little bit backwards for number 6. Look at number 6, please. If you know that OP was 3 and OP prime is 9, how could you use that information to find the scale factor? So for number 6, we're going to pretend that we do not know the scale factor is 3. We don't know that. We're pretending that we do not know. But we do know OP, and we know OP prime. Can we find the scale factor with that information? Yes, we can. Because we can say, okay, this part is 3, and this part is 9. How much did it grow? You can see, well, if you multiplied to find 9, then to find the scale factor, you do the opposite, you divide. Let me show you. Remember, OP prime equals R times the original. The prime equals the scale factor times the original. But this time we don't know R. But we do know that OP is 3. We know OP prime is 9. And R is missing. This is algebra, which I know you did this kind of algebra in 5th and 6th grade. So if you know OP prime and you know OP, you can find the missing R. You just divide both sides by 3. Or this right here, probably mental math for a lot of you. Something times 3 equals 9. You'd know 3 times 3 equals 9. But if you want to show the algebra, you do this divided by 3. And 3 divided by 3 turns into 1. So on this side, we get R times 1, which is just R. But if we change this side, we have to change this side also. So we do 9 divided by 3. And 9 divided by 3 is 3. So R equals 3. So if we know this OP and OP prime, how do we use the information to determine the scale factor? You just divide OP prime by OP to find the missing scale factor. It's a one-step algebra problem. You divide so if you multiply when you have the scale factor, when the scale factor is missing, you divide. You do the opposite. Hopefully you understood that. Hopefully it made a lot of sense. It is pretty basic with scale factors today. They just want you to get the idea of practicing and multiplying and seeing how things can grow and shrink. Let's look at some of the work today. Let's look and see what you're doing for practice today. So turn the page, go to page 4. Page 4 is the lesson summary that you can read if you like to. It is basically summarizing everything we talked about, how OP prime is R times OP right here. R times OP, it makes OP prime. And then on page 5, the next page is the exit ticket. Just slide that to the back. We'll talk about that last. Page 7 and 8 are your homework helper, where they give you example problems just like the problem set. These problems are just like the problem set, but they give you the answer and they explain how they think about it. So if you get stuck on the problem set, look at the homework helper. It will be useful. But I'm going to look at the problem set with you right now. I'm going to explain some of it to you to kind of help a little bit. So number 1 on the problem set says, let there be a dilation from center O. So O is the center right here. Then the dilation of P equals P prime. So here's P and here's P prime. And the dilation of Q equals Q prime. So here's Q and here's Q prime. There's O right here. What do you know, or what can you determine about the scale factor of the dilation? Now, they don't have numbers on here. You just know P is dilated to make P prime. Q is dilated to make Q prime. So it's basically asking, what kind of dilation is this? So for this, you might want to look at your notes and say, okay, well, what kind of dilation? Is it a growing dilation? Is it a dilation where they stay the same size? Or is it a shrinking dilation? What kind of dilation is it? Well, just look, I'll do this one for you. Look at it. Here's P, here's P prime. How far, what is the difference between the distances from the center? So P prime is farther away from O. P is here, P prime is farther away. So the distance grew. And Q prime is farther away. So the distance got bigger. So what do we know about the scale factor when the distance gets bigger? Well, in your notes, when the image grows, when the image gets bigger, we know the scale factor has to be greater than 1. So that's what this means. What do we know about the scale factor? The scale factor is greater than 1. Do we know what the scale factor is? No, because they did not give us any numbers. But we do know it's greater than 1 because the prime is farther away from the center. It grew farther away, so it's greater than 1. Just like that. Now for number 2 on the problem set, right underneath that, it's the exact same question, except for this time you have to pay attention. You probably should pay attention to how they set it up, because we still have center O, we still have point P, except for this time P prime is closer to O, and we still have Q, but this time Q prime is closer to O. So because the images, the primes, are closer to the center, the distance shrunk. What does that tell you? What do you know? What can you determine about the scale factor when the prime is closer to the center? I'll let you write the answer down yourself. You can always remember, I do the work online and I post it on the Google Classroom, so you can always check your work there. Moving on to page 10, number 3 on your problem set. It says, let there be a dilation from center O. So we have center O. And the scale factor is 4. R equals 4. So they tell you the scale factor. They give you the center. They tell you OP is 3.2. OP is 3.2. And they tell you OQ is 2.7 right there. So they give you the center, they give you the lengths, they give you the scale factor, and now they're asking, use that information to find OP prime for part A, and for part B, find OQ prime. So this is what we did in the exercise today. So if you need to see again what I did, this for number 3, you can look at exercise 2 through 6 on page 3. That'll help you. After you do the problem set, please remember to check your work with my work that I post on the Google Classroom. You have one more question for the problem set. This time, it's going to be a little bit different. Let there be a dilation from center O. So here's the center O with scale factor R. Uh-oh, they don't tell you the scale factor this time. But they do tell you, they do give you some information. So they give you OA is 3. They give you OB is 15. They give you OC is 6. And they give you OB prime is 5. So they give you a lot of numbers, a lot of information on this. The first thing they want you to do is use OB prime and OB to find R. So part A is asking R equals what? What does R equal for part A? You have OB, you have OB prime. How does OB turn into OB prime? You know, by the way, it shrunk. It's not getting bigger. OB got smaller to make OB prime. So what kind of R is it? Is it greater than 1, less than 1, or 1? What is R? And then after you have R, find OA prime and find OC prime. Use R and OA to find the prime. Use R and OC to find OC prime. And remember, my work is posted on the Google Classroom. It is there to help you. It is there for you to check your answers. I am also here all day to help you. If you have questions, you can ask me about it. But after you check your answers on the problem set, your exit ticket is what you're going to work in and take a picture of and turn it in online. So number one, why do we need a better definition of similarity than same shape, not the same size? Remember what we talked about math and what math is and what math needs. Why is this definition not good enough? In other words, for number 2, they give you the scale factor and they give you OP. They want you to find OP prime. Exit ticket number 3, they do not give you the scale factor. They give you OP and they give you OP prime, and you have to find the scale factor. These answers will not be posted online, but if you do the problem set, if you check your work, and if you ask me for help when you need it, you should not have a problem with the exit ticket. Remember to take a picture of it and turn it in on the Google Classroom. Try your best, ask for help if you need it, and I will see you for the next lesson. Have a great day.